Good morning, everyone. In the last lecture, we have discussed the graphical method for solving linear programming problem in a standard form and also with mixed constraint problem with maximization of profit and the minimization of cost objectives. See, the graphical method is the one of the easiest way to solve a small linear programming problems. But this is useful only when the decision variables are not more than 2. What happens if we have more than 2 decision variables? See, in this case, it is not possible to plot the solutions on the two-dimensional graph. And if we have more than 2 decision variables in the given problem, then the graphical method is not a practical to solve the linear programming problem. And sometimes the solution can be found graphically by using its dual. So thus today we will discuss the concept of duality in linear programming, and also we will discuss the mathematical formulation of dual problem. So let us look at what actually the duality means. See, we have a two concept, that is primal and dual, related to the theory of duality. See, any linear programming problem can be converted into a corresponding pairs, which is most popularly known as it is dual, which can give same feasible solution of the objective function. See, every linear programming problem has a corresponding problem which is popularly known as it is dual problem. So the given original problem, whether it is maximization or minimization, doesn't matter, it is generally called it is a primal problem. That is, if the original problem is maximization, for example the maximization of profit, then its dual is the minimization, that is minimization of cost sometimes. So if the original problem is minimization, then its dual will be the maximization. So thus the optimum value of the primal objective function is equal to the optimal value of corresponding dual objective function. So both are equal. So the dual problem is derived from, actually it is from the primal problem only. So in order to find out dual, of course we need a primal problem as well. So sometime the dual problem solution may be easier than the primal problem solution. So in this particular situation, we are generally using the dual especially for finding an optimal solution. So the solution of a dual problem leads to the solution of the primal problem, and thus the efficient computational techniques can be developed through the concept of duality. So the dual of dual, see, the dual of dual is a primal problem. That means if we take the dual of a dual problem, we will get back the original primal problem that we started with. So this duality relationship is actually the fundamental concept in the linear programming problem and the optimization theory as well. So now we are going to find the mathematical formulation of duality, or with given primal problem, how to find its dual. See, the first step is that if the objective function in the primal problem is to be maximized, then its dual is minimized. Or in otherwise we can also say that if the objective function in the primal problem is minimization problem, then its dual will be the maximization problem, just opposite of that. So the objective function in the dual problem correspond to the opposite optimization direction of the primal problem. So if the primal problem aims to maximize certain objective function, then its dual problem aims to minimize its corresponding objective function, and also just opposite of that can also be taken. So this is the first step, how to convert primal into a dual. For example, we have a primal problem is given here. That is primal problem here we want to maximize a particular value. That is, for example, we are going to consider that profit maximization example. So here z is equal to profit which we want to maximize, which is equal to 3x1 plus 8x2, which is the maximization value we want to find, subjected to the constraint that are x1 plus 2x2 less than or equal to 2, 2x1 plus 8x2 which is less than equal to 6, then of course the decision variable are greater than equal to 0, that is x1 and x2 both are greater than equal to 0. See, this is the standard form of a maximization problem. We have an objective function and also here the equality sign, inequality sign which is less than or equal to sign here. So this is the standard form of a maximization of problem. This given problem we are generally going to consider that it is a primal problem. This is generally known as it is primal problem because this is our original problem that is generally known as that is primal. Now from the given primal problem we want to find its dual. See, as what first step we are discussed that if our objective function in the primal problem is maximization, then its dual will be its minimization. So here we have a maximization problem. For example, it is maximization of profit. Then here we want to minimize. For example, it is minimization of cost. So our objective function is changed. That is, it was earlier it is maximization of profit. Now from its dual, it is the minimization of cost. So this is the preliminary steps toward the conversion of primal problem into a dual problem. See, after the first step, the another step is that the column vector of the constant from the primal constraint is transposed to a row vector of the coefficient for the objective function in the dual, which means that in the process of constructing the dual problem from its primal problem in the linear programming, see the coefficient of the objective function, in the dual problem are derived from the constant of the primal problem's constraint. Should be kept in mind. See, it is, of course, we know that each constraint in the primal problem consists of a linear combination of decision variables, that is the coefficients and its constant terms. So when we are going to formulate a dual problem, these constants from the primal constraint are transposed into a row vector which become the coefficient of the objective function in the dual. So we are going to consider that part. See, our original function is primal. The first step we are completed, that is maximization, we are converted into the minimization problem. Now see here, the constant of the given constraint, see it was 2 and 6. This is the constant of the given constraint, or this constant is going to convert the coefficient of the objective function. See here, we are going to consider this 2 here, 2y1. Instead of x1 and x2, we are going to denote in terms of y1 and y2 now, from its primal to its dual. So here, this particular constant, that is the from the constraint number 1, it is 2, and from the constraint number 2, it is 6. These two constants are now become the coefficient of the objective function, especially in the dual problem. So here the minimization of cost, which is equal to 2y1 plus 6y2. See, this constant is now become the coefficient of the objective function. So this is the second step. See, after finding this particular step, that means the finalization of our objective function, the third step is that the inequality sign of the technical constraints are reversed. But at the same time, the non-negativity constraints on the decision variable, that is always maintained. So what we are going to change here? Here the inequality sign of the technical constraints are going to reverse. So when we are formulating dual problem from its primal in linear programming, see, there is a specific rule regarding the transformation of constraint, that is the inequality sign of the technical constraint are reversed. This reversal of inequality sign actually ensure that the direction of optimization in the dual problem is the opposite to that of primal problem. So however, of course, the non-negativity constraint on the decision variable that are always maintained in both primal as well as in the dual problem, which means that both problems, the decision variable must be non-negative. So now from the given example, this is our primal problem. So here, see, constrain the inequality which is less than or equal to in the both constraint. Now we are going to reverse this particular constraint. See, now in the dual problem, it will be greater than or equal to, just opposite of that. Here it was less than equal to, now it is converted into the greater than or equal to in the both constraint, just opposite of that function will be work. So at the same time, we assert that the non-negativity constraint on the decision variable is always maintained. Here our decision variables were x1 and x2. Both are greater than equal to 0. Here our decision variables are y1 and y2, which are also considered as the greater than or equal to 0. That means the non-negativity constraint on the decision variable are always maintained, but only the inequality sign of the technical constraint that can be reversed. So it was less than equal to here. Now in the dual problem, it became the greater than or equal to. Now the fourth step is, see, the row of the coefficient matrix of the constraint in the primal are transposed to the column for the coefficient matrix of the constraint in the dual. Which means that when we transpose the coefficient from the primal problems constraint to form the coefficient of the dual problems constraint, then we basically exchanging rows for columns and columns for rows. So this is because the relationship between the primal and the dual variables are captured in the form of the constraint and the objective function. So we are going to conduct this particular step. See, from our primal problem, see the coefficient of the first constraint, that is 1 and 2. The coefficient of the second constraint, that is 2 and 8. Now we are going to transpose these coefficients here. This 1, 2, now here it will become 1 and 2 here. It will become the coefficient of y1. Similarly, this 2 and 8 will now become, it is 2 and 8. It is just opposite. You are going to convert this row into the column. So the coefficient of 1 and 2, it now became, that means 1 and 2, the column now became this particular row is now became the particular column, and the second row coefficient are now became the second column. So we can write it is y1 plus 2y2 greater than or equal to. Then what is here that we will discuss in the next step. So 2y1 plus 8y2, which is also greater than equal to. So both variables are non-negative. Then after finding this step 4, the next step is, that is, row vector of the coefficient in the objective function in the primal problem is transposed to the column vector of the constants for the dual constraint. So here the coefficient of the objective function, that means earlier it was the profit maximization problem, that was the objective function, its coefficient now will become the column vector constant for the dual constraint. So we are going to consider that particular part. See, what was the coefficient of or row vector coefficient of the objective function? See, this coefficient is 3 and 8. Now this 3 and 8 now will become or transposed to the column vector of the constant for its dual. So here for the constraint, these two coefficient, that is 3 and now 8, will become, it is column vector for the constant for the dual. So here it will be greater than or equal to 3 and greater than equal to 8. And at the same time decision variable will be maintained, that is greater than equal to 0. So now the conversion is completed, or mathematical formulation of dual is completed. From our primal problem, we are changed everything into a constructing a particular dual problem. So it was related to the maximization problem, so its dual will be the minimization problem. Now we are going to consider the another example. See, we explained in the earlier case, that is example of a maximization profit as a primal problem. Now we are going to consider the another example that is related to the minimization problem as a primal and we are going to convert into its dual, that is the maximization of profit. So the same process will be maintained. Once again I am repeating here, that is the step 1. That is, if the objective function in the primal problem is maximized or minimized, then the dual is minimized or maximized. So in this case, what we are going to consider the example, that is the minimization problem we are going to consider. So our objective function in the primal problem is minimization, and its dual will be then it is maximization. Consider one example. See, our primal problem, that is minimization of cost, which is equal to 20x1 plus 30x2 plus 16x3, subjected to the constraint, that is 2.5x1 plus 3x2 plus x3, which is greater than or equal to 3, x1 plus 3, x2 plus 2x3, which is greater than equal to 4. See, this is the standard form of the minimization problem. Here the variable x1, x2, x3 are the greater than equal to 0. So we have a standard format of a minimization problem here. This is our primal problem. Now we are going to convert this primal problem into the dual. And the first step we said that the objective function in the primal problem is minimization, then its dual will be maximization. So I am going to change here the minimization of cost into a maximization of profit. Okay. Now after this particular step, now we are going to move to the second step, that is column vector of the constant from the primal constraint transposed to a row vector coefficient for the objective function in its dual. So let us consider what are the various constant of the constraint. So that can be converted into the coefficient of the objective function. So as per our example, we have a column vector of the constant, that is 3 and 4 here. This is considered as the column vector of the constant in the primal problem. Now this 3 and 4 now will become the coefficient for the objective function in its dual. So we have a dual is maximization problem, that is maximization of z is equal to, so instead of x1, y, x2, x3, we are going to change the variable name as y1, y2. So here the coefficient will become, see, this column vector constant will become the coefficient here. So it will be 3y1 plus 4y2. So this is the second step. Then the third step is the inequality sign of the technical constraints are reversed. But at the same time, we are going to maintain the non-negativity constraint on the decision variable. So here in the primal problem, it was greater than or equal to. See, in the both constraint, it is greater than or equal to. We are going to change or reverse this particular inequality sign from the greater than or equal to into the less than or equal to. In the 3 variable we have, so here we have a converting into a 3 constraint. So we have a 3 inequality sign which is less than or equal to in the case of a dual, that is maximization problem. At the same time, we are going to maintain, that is y1 and y2, that is decision variables are greater than or equal to 0. Now after the third step, see, the next step is the row of the coefficient matrix of a constraint in the primal are transposed to the column for the coefficient matrix of the constraint in the primal problem. So the coefficient of the constraint where we are going to convert, that is we are going to take its transpose, then it will become, see our example, see it is 2.5, 3 and 1. Was the coefficient of x1, x2 and x3. This is the row, and that we are going to convert in the form of column. So it will become, see, 2.5, this 3 will come here, and here the coefficient 1 will come here. And similarly, the coefficient of the second constraint, that is 1, 3 and 2. Now I am going to convert in the column, that is 1, y1, 3, y2 and 2, y2. Okay, so now we are just the coefficient of matrix of the constraint in the primal problem into the column coefficient for the matrix in the dual problem. Now after this particular step, the last step is that the row vector of the coefficient in the objective function in the primal are transposed to the column vector of the constant for the dual constraint. So how it will be constructed? See, what are the coefficient of the objective function in the primal problem? See, the coefficient of the primal problem, that is minimization of cost, that is 20, 30 and 16 for the variable x1, x2, x3 respectively. So here, now this coefficient we are going to convert into the column vector of the constant in the dual. So it will be, see, it will come here in this particular part, that is constant for the dual, especially for the constraint. So this 20 will become here, that is less than or equal to 20. Then this 30 will come to the second constraint constant, that is less than or equal to 30. And this 16 will becomes out the constant for the third constraint, that is less than or equal to 16. So our decision variable, that is y1 and y2, which are greater than or equal to 0. So the conversion is completed now. We have a dual, that is maximization problem, but at the same time the primal problem was related to the minimization. So we are converted into the dual problem. Now we can solve this. This is ready for solution, that is especially you can go for the graphical method. Now see, we are going to check the relationship between the primal and dual. See, the first point is the number of constraints in the primal problem is equal to the number of duals in the variables. See, the number of constraints in the primal problem is equal to the number of dual in the variable, that is vice versa also. This just opposite can also be considered. This is the first relationship. Now the second relationship saying that if the primal problem is the maximization problem, then the dual problem will be minimization. And similarly, if the primal problem is the minimization problem, then the dual problem will be the maximization problem. So this is also another relationship. The third one, if the primal problem has the greater than or equal to type of constraint, then its dual will be less than or equal to type of constraint, and vice versa. That means if the primal problem is having the less than or equal to type of constraint, then its dual will have the greater than or equal to type of constraint. This is also another relationship between the primal and dual. And the fourth one, that is the profit coefficient of the primal problem, that is the coefficient of the primal problem objectives appear to the right side of the dual problems constraint. That means it will become the constant of the dual problems constraint. And the last one, that is the row in the primals become the columns in the dual, and the column in the primal problem will become the row in the dual, and just opposite of that can also appear. So these are the various relationship, and at the same time the last one which we are going to consider here, that is all the primal and dual variables, that is decision variables, either in the case of a primal problem or in the case of a dual problem, must be greater than, or sorry, it must be non-negative, that means it is greater than or equal to 0. So these are the major relationship between the primal problem and its dual. Now we want to solve a particular question, that is solve the linear programming problem graphically. Now let us consider this particular example, that is primal problem. See, the graphical method here, the minimization, that is P, which is equal to 20y1 plus 30y2 plus 16y3, subjected to the constraint, that is 2.5y1 plus 3y2 y3, which is greater than equal to 3, y1 plus 3 y2 plus 2 y3, which is greater than equal to 4, and all the decision variables are greater than equal to 0. Now if you go for finding the solution of given minimization problem by using the graphical method, we can't represent it practically because we have a 3 decision variable here, that is y1, y2, y3. See, the graphical method is one of the easiest method, no doubt. We solve, especially in the case of it can be applicable in the case of a small linear programming problem. But this is useful only when the decision variables are not more than 2. What happens if we have a more than 2 variable, just like this particular given example? In this case, it is not possible to plot the solution on the 2-dimensional graph. So if we have a more than 2 variable, then we can use another useful method, that is for finding the solution of linear programming problem, which is much popularly known as it is simplex method, that we will discuss in the upcoming lectures. But we have another option, that is we can convert or we can solve this particular problem by using its dual. That means it is possible to solve the given linear programming problem involving this type of 3 variable case that have only 2 constraints. We have only 2 constraints. Then we can take its dual. And we can solve the same graphically. So if you are going to consider this particular, the dual of the given primal problem, then it will become maximization of, for example, instead of y1, y2, y3, I am going to consider the decision variable are x1, x2. So here the constraint, the constant in the constraint, that is 3 and 4, now will become the coefficient. Of course, the minimization problem will become the maximization problem. So we have a 3x1 plus 4x2, which is subjected to the constraint, that is we are going to convert, that is the coefficient of the variables in the row into the column vector. So here it will become 2.5, 3 and 1, that I am writing here in the form of a column wise. So it will become 2.5x1, 3x1 and 1x2. So here also the coefficient, that is y1, that is 1, 3 and 2, we are going to write in the column model, that is here 1, 3 and 2, especially the coefficient for x2. Then the inequality sign, which was in the primal problem, it is greater than equal to. So here it will become the less than equal to. And at the same time, the non-negativity constraint, that is the decision variables, always be the positive, that is greater than or equal to 0. Similarly, this coefficient of the objective function 20, 30 and 16, that will become the constant for the constraint, especially in the case of a dual problem, that is 20, 30, 16. So it will become less than equal to 20, less than equal to 30 and less than equal to 16. So the dual problem, it is actually offering the alternative representation of the original primal problem, and this alternative perspective can sometimes simplify the problem structure, or we can say that they reveal hidden relationship between variable and constraint. This primal problem was unable to solve the graphically, but its dual can be solved by using the graphical method, because we have only two decision variable here, that is x1 and x2, so that we can go for the two-dimensional graph, and accordingly you can solve this particular problem by using its dual. But there are certain problems related to the duality as well. See, the duality concept in the linear programming, that is no doubt, it is a very powerful and provide a valuable insight, but it does not necessarily means that solving the dual problem is always practical or efficient way to find the solution to the primal problem. So there are certain reasons why the directly solving the dual problem might not best solution. Why it is so? Because one of the major reason, because of its complexity. The dual problem might be a complex as the primal problem, or even more complicated. So solving the dual problem could involve dealing with a large number of constraints or the variable and making it computationally intensive. So the system may be, if you are going to convert the primal problem into the dual, it may be complex. Then another problem, see, it is related to the objective mismatch. That means the objective function of a dual problem is derived from the constraint of the primal problem and vice versa. So therefore, the objective of the dual problem might not align with the goal or objective of the decision makers. So at that particular point of time, the entire calculation will be misinterpreted. Similarly, again the problem is related to the interpretation of the solution. See, the primal problem and the dual problem might have different interpretation and the implications as well. So while the primal problem typically represent the decision making or the optimization problem in its original context, then the dual problem might have different economic or operational interpretation. So at that particular point of time, if you go for interpreting the dual, then it will lead to the misrepresentation of the entire problem. So let me conclude here. We have discussed today the differences between primal problem and the dual problem in the linear programming, and also we discussed the formulation of dual problem from the given primal problem. Actually, it established the connection between the solution of the primal and the dual problems. I hope it was clear to you. In the next lecture, we will discuss the solution of linear programming problem by using the simplex method. So we'll see in the next lecture. Thank you.